Start recording. So we want the pH of 0.0025 molar CaOH2. Now CaOH2, what kind of a substance is that? That is a base. And in particular, what type of element is calcium? It's a metal. So we have a metal hydroxide. And what do we know about metal hydroxides? They are strong. And they don't behave like acids where if you have a strong acid, like if you have H2SO4, only one of the protons comes off strongly. Yes, and then the second one comes off a little bit less. But metal hydroxides don't do that. They dissociate completely, okay? So if you have CaOH2, CaOH2 completely separates into Ca2+, and how many hydroxides? 2 hydroxides. So if our concentration of CaOH2 is 0.0025, then the concentration of calcium, we have a 1-to-1 ratio. Concentration of calcium is also going to be 0.0025, but what's going to happen with the concentration of hydroxide? Yeah, we're going to have 2 times 0.0025, and so that will be 0.005. Now, if we want to find the pH, I would start probably easiest to find the pOH and then transfer that into pH. So this is hydroxide. So our pOH is the negative log of 0.005. 0.005 log, and we get 2.30. Then pH is 14 minus 2.30. 11.698, which is 11.7. Sorry, I didn't round off my number. Anyway, yeah, 11.7. So answer is D. Yes. 30? Sure. Number 30, we need the pH of 2 molar benzoic acid. Now, anytime you have a substance, you need to ask yourself, is it an acid or a base? Well, this one's easy. It's an acid because it says acid. Okay. And the other thing you have to ask yourself is it strong or is it weak? Benzoic acid is weak. Okay, so here's benzoic acid. And if it is weak, do you remember what happens to the weak little old lady? What does she do?
Rice.
Rice and Ka. Now, are you going to bother with an entire rice table for a multiple choice? You certainly can. Okay, I will just do a little quick one over here. So we have R, I, C, E. I'm just going to call this HA because that's way too long to write out. Does that Makes sense. So we have HA in equilibrium with H plus A minus. This is 2. These always start at 0. These go up. This goes down. 2.0 minus x, x, x. And we are going to assume x is insignificant. Now, am I going to write all this for a multiple choice question? Not if I don't have to. If I can just know that I take my initial concentration of the acid and put it on the bottom of my Ka expression, and if I know that H and A are both equal to x, then as a shortcut, what I can do is I can say that my Ka value, which is 6.4 times 10 to the, no, 6.5 times 10 to the minus 5, is equal to x squared over 2. And now that becomes a fairly straightforward calculation. Yes? So if you need to do a whole rice table to get there, that's fine. Maybe leave that question till the end, though, because it's going to cost you a lot of time if you need to do that. If you can just see that, oh, I know how this works. I know that in the written response, I'll lose marks if I don't write this. But I know that in multiple choice, I can just go bam straight to there, where I have my x over the concentration of the acid is equal to Ka. I'm good to go. Is that good? Okay. And then, of course, x would be the hydrogen, and you'd have to take the negative log to get the pH. Yeah? All right. Yes? We can do that. I just want to see it. Does anyone in here have anything? Yeah. 7 written. Yes. Oh, 7 written is tricky. I'm probably not going to give you a question like this. Do you want me to go over it? I can do it real quick. Okay. All right, so we have a solution with pH 4.20, contains twice as much conjugate base as acid. So we have, it's 4.20, therefore, and it's told that it's a monoprotic acid, HA, in equilibrium with H plus and A minus. I'm going to do a rice table because always rice. And I know that my concentration of H plus is equal to 10 to the negative pH, which is 10 to the negative 4.2. So that is 6.31 times 10 to the negative 5. So I have 0 and 0 and 6.31 times 10 to the negative 5 and 6.31 times 10 to the negative 5. And now you might say, hang on a second, Miss Spence, we don't have an initial concentration, but we know that we have twice as much base as acid. Twice as much base as we do acid. So how much acid do we have? 6.31 times 10 to the minus 5 divided by 2. And now you have your equilibrium concentrations. You don't actually need to fill in the rest of the rice table. I would just cross it out. And then there you go. Okay, but you won't get a question like that on this test. You don't have an initial concentration, so you can't. Do you know what I mean? I would just be like, okay, this irrelevant. I would go like this. I'd be like, oops, irrelevant. Oops, irrelevant. You know what I mean? I'd be like, okay. So I'd say this isn't, yeah. Yes, because I can't do anything with an I and a C because there is no initial for HA. Yeah. Okay. We got anything else? Yes?
44.
44. Okay, consider the following equilibrium. Now, this is one where you need to make sure you have read the question because I've had numerous people ask me about this one because HOI is not on your table of acids. Okay, we have HOI plus F minus, this should say minus, I need to fix that. In equilibrium with OI minus and HF. Which of the following describes the relative strengths of the acids and the bases? So there is information in this question that will let you figure that out. What does the question tell you that will let you figure out who is stronger and who is weaker? It tells you that the reactants are favored. Yes? And if the reactants are favored, that means that these guys, are they both stronger or are they both weaker? They are both weaker. And that means that these guys are both stronger. And who are the acids? This is our acid because it's got the H. This is our acid. This is our base. And this is our base. So that means our stronger acid is HF. And our stronger base is OI minus, which means our answer is B. Yes? Then you cannot solve this problem because you don't have enough information. Yeah. I could give you a KEQ value, which would also tell you whether reactants or products were favored. So if I gave you, let's say I had a question like this, and I gave you KEQ is equal to 3 times 10 to the 3. What does that tell you? That tells you products are favored, and then you could go on and do the same sort of thought. Now, it wouldn't be that because reactants are favored, but anyway. Good question. Yes? 57, yes. Okay, 57. We have this blue equilibrium here. Okay. And what changes occur to H3O plus? Now remind me, or remind your partner, tell your partner, what is the name of H3O plus and what is it the same as? H3O plus is called hydronium. And what is it the same as?
H+.
It's the same as H plus. Excellent. All right. Now, we are going to add some NaOH. We are dumping this into a beaker full of water, yes? Because what do we have here? We have water. So what happens to NaOH when we put it into water? It dissociates. Now, is it a partial dissociation or a full dissociation? Full. How do we know that? It is a metal hydroxide, and metal hydroxides are strong bases, so completely dissociates. Now we're going to look at those two ions, and we're going to say, Do I care about the Na plus? Do I care about the OH minus? Do I care about both of them? How do each of those affect the blue equilibrium? What effect does sodium have on the blue equilibrium? Nothing. Sodium doesn't react with anything there, right? Sodium ion, very unreactive. How about hydroxide? It matters because guess what? We have it here. So if we have added NaOH, what have we changed? We've changed what is the stress? We have increased
The basicity. The increased concentration of OH.
We've increased concentration of OH. Yes, we have increased the basicity, but this is going to let us predict a shift. Yes? So if we increase the concentration of OH, which way does that equilibrium shift? Shifts to the left. And what is the result of that shift on the concentration of H3O plus? Yeah, H3O plus is going to go down, okay? And if H3O plus decreases, what happens to pH? pH increases because they go backwards of each other. Yeah. 14 written? Yeah. Okay, that's supposed to say KW, not K2, for starters. Okay, the 2 and the W use the same finger. Okay, so I need to fix that. Fix. All right, now we need to determine the pH of water at 10 degrees Celsius. Now, what is KW equal to? KW is equal to, not the number, but the formula.
H times OH.
It is equal to the concentration of H times the concentration of OH, because it is the equation for the dissociation of water, okay? Now, if this is water, what do we know about the H and the OH?
Equal to each other.
They are equal to each other. And if they are equal to each other, what can I do here? I can make it H times H. Yes, so I have KW is equal to concentration of H times concentration of H. So how could so I can plug this in now, I can say 2.95 times 10 to the negative 15 is equal to concentration of H plus squared. Yes, so I've substitute KW, and now I have H plus squared. How do I find H? Take the square root. Okay, so we have 2.95 times 10 to the negative 15. We take the square root of that and we get 5.43 times 10 to the negative 8 molar. And then we need to find the pH. So pH equals negative log of H, which is the negative log of 5.43 times 10 to the negative 8 log. And we get 7.265. And how many sig figs do we want? We want 3 sig figs.
After the decimal.
And so because it's a p value, remember whenever you have a p, we only count digits after the decimal. So that's 3 sig figs there. So that is our correct answer. Okay. Now, state whether water at this temperature is acidic, basic, or neutral, and explain. It is neutral because, damn it, it's water. Okay. No, but you could say that it is neutral because H and OH are the same. Yes? H plus equals OH minus. That's the definition of neutral, is that those two equal one another. Good question. Yes? 11 in the written? Yeah. This is a good one. We did this in the other class. Okay, first thing we need to decide is what on earth does the word predominant mean? Because I know for a lot of people, that is the sticking point. They're like, what? What is that word? It is a really common word in chemistry. Okay, so we're going to learn the meaning of the word where'd you go? There we go. Predominant. Predominant means main. So we want to find an equation to represent the main reaction. Yeah? When HC2O4 is mixed with HSO4 minus. So, easy thing to do is to start by saying, I need an equation. Who are my reactants? And just the two things that are right there, right? Okay, so that part is easy. So A, we have HC2O4 minus plus HSO4 minus. Now, you've met reactions like this before. You've got H's and negatives. What do you need to do? Yeah. Exactly. And you know what? It says justify your statement by comparing Ka values in the next step. So we're going to grab those while we are at it. Okay. So let's go find the Ka value for HC2O4 and HSO4. HC2O4 is in green here. There's its Ka value, 1.2 times 10 to the minus 2. And HC2O4 minus, its Ka value is 6.4 times 10 to the minus 5. Now, we are being asked to use the Ka values, but if you were not asked to use them, you could just say that, what could you say? HSO4 is stronger than HCO4, therefore HSO4 will act as the acid and HCO4 will act as the base. Okay, let's go back here. So this was 1.2 times 10 to the minus 2. That's the Ka value. And over here we had 6.4 times 10 to the minus 5. And what that means is that H2SO4 is stronger. Now, am I going to have a one-way arrow or a two-way arrow?
Two-way arrow.
Two-way arrow. And who are the products going to be? Well, if this one is stronger, it's going to act as the acid. And this one is now going to act as the base. Okay, so please write your products for that reaction. So now what I'd like, well, why does it jump around on me? It's like crazy. Okay, there we go. Now what we're going to do is we're going to justify our answer, our statement, by comparing Ka values. Now, one of the things I would like you to work on is writing clear and coherent answers. And in order to do that, I'm going to encourage you to use point form. Yes? Because that way there are less words to get tangled in. Yes? So, what's the first thing that you could say if you're justifying your answer in terms of the Ka values?
The K of HSO4 is larger than the K of HCO4.
Yes, and if I have written these up here, I can just write that. If I hadn't written them up there, I would probably do like 1.2 times 10 to the negative 2. Yeah, I would throw that in there. Is greater than, and you don't even have to write like is greater than, you can just write is greater than Ka of HC2O4 minus. Excellent. Point number 1.
Because HSO4 has a stronger, it has a higher Ka than the K of HC2O4. HSO4 will act is stronger, which will therefore.
That's a lot of words. I want you to realize that you have just told me once again that the Ka of this one is stronger than that one, is bigger than that one. So you've reiterated that. So we don't need to say again that Ka of this one is stronger than that one. We can just say, therefore, yeah, if you want to, I'm going to put an extra one in there. This is like optional. HSO4 minus is a stronger acid than HC2O4 minus. So this part here is optional because for the most part, people should understand that the bigger the Ka value, the stronger the acid. Okay. But if they gave you a 3-mark question, you could throw that in there for extra, right? So then you're just going to make the statement, therefore, what happens next? Tell your partner what you think.
HSO4 acts as the phosphoric acid, building a proton to HC2O4.
Okay, other than the fact that there were more words there than you needed, how could you shorten that? How could you tighten that up?
HSO4 acts as the acid.
And
donates a proton.
H.
2O4 acts as the base.
Okay, so we're going to work on tightening up our language. Okay, not that you would get it wrong if you wrote that. You've just spent a lot of time doing it. You know what I mean? So that's nice. That's B. Identify a conjugate acid-base pair.
SO4 and SO4 are one conjugate acid base pair.
Okay, I would just write
SO4 and
SO4, 2 minus, done. Yes, that's all you need. Now, should you write the other conjugate acid-base pair? Let's read what the question says. Identify a conjugate acid-base pair. If you start trying to give me 2 conjugate acid-base pairs, it's possible that you might write it in such a way that it becomes confusing as to which one you think is which and who is with who. And do you know what I mean? If you're asked for one, give me one. Yes? Okay. You could have, in a different life, written HC2O4, 2 minus, and H2C, C2O4. But either this or that, not both. Yes? Okay, good. And hopefully predict whether the equilibrium will favor the formation of reactants or products. And then it says explain. So figure out whether it's going to predict, favor reactants or products, and then think about how you would explain that.
And then strongly this side. So, okay, let's put phrasing. So bullet point 1. Okay, so H2C2O4. The Ka of H2C2O4 is greater than the Ka of HC2O4. Second bullet point. Yes. H2C2O4 is stronger than HC2O4. The second bullet point. Third bullet point. This. Therefore, the reaction will be favored because H2C2O4 produces is a stronger acid, which makes more is a stronger acid. Oh, okay. Good enough. Okay. Shall we try this? Okay, let's start with Ka, because this question seems to like Ka, so let's talk Kas. Ka of who? Ka of H2C2O4.
Because this is our other acid, because now we're comparing our 2 acids, right? So Ka of H2C2O4 is
greater than Ka of HC2O4.
Of who?
HSO4.
HSO4, because we need to compare our 2 acids, yes? HSO4 minus therefore, and sorry, go ahead. H2C2O4 is the stronger acid. Very good. And therefore, now this is again optional. the reverse reaction is favored. Right? Because, you know, the stronger acid is pushing more. You're not going to say that, but you'll just be like, the reverse reaction is favored, and therefore reactants are favored. Yes.
Okay.
So basically what's happening is that this is our stronger acid. So it's better at giving away protons. So you'll end up with more of the stuff where it gave away a proton. Does that make sense? It's better at giving away protons. And HSO4 is not as good at giving away protons. So you end up with less of that turning into its base. Yeah. Alrighty. That was a good question. Thank you guys for asking that one. Yes? You can just say H2CO2O4 is stronger than, is the stronger acid, is stronger than HSO4 minus. You should mention the two species, but you could just say one is stronger than the other because they didn't ask you to mention Ka there, so that's fine. Yeah. Other questions? Yeah. Yeah. Yes. Room temperature, then Ka would be 1 times 10 to the negative 14. pH would be 7, and it's still neutral. Because if it's water, it's always neutral. Yeah, H and OH are, if it's pure water, H and OH are always the same, it's always neutral. Doesn't matter the temperature. Doesn't matter the pH, doesn't matter the pOH. Okay, what will happen here is that our pH is 7.265. Our pOH will also be 7.265, and that means our KW will actually be like 14 point, I don't know, something, you know, 5-ish. Yeah, yeah.
Since the pH of pure water is different with different temperatures, does that mean like neutral pH is different?
Bingo. Yes. At different temperatures, neutral pH is different. So at 10 degrees, neutral pH is 7.265. Yeah, absolutely. Good question. ¿Algo más? What's Jenya doing? She's like crazy with her thumbs there. Oh my gosh. I went to the symphony a while ago, maybe like a year ago, and I was up on like the second floor looking down at the people in the lobby, right? And there's this guy walking across the floor, texting away, but he's looking where he's walking. And I'm like, how can you even do that? Like, how? Anyway, no, it's beyond me. I'm too old. I have my phone in one hand and I'm like desperately plucking out the letters one by one and spelling them wrong and not using the select word, and I don't know, it's just pathetic. So anyway, other questions? Yes? 16?
Yeah.
Yeah. Written?
Yeah.
Yeah. Okay, write the chemical equation showing an amphiprotic anion. So we need a substance which is both amphiprotic and an anion, and we need it reacting as a base in water. So amphiprotic means that it needs an H and it needs a negative charge. Yes? So let's go here, pick one, anyone. I mean, you could pick this one, but it's really big and long, so I probably would not choose that one. I'd pick something smaller, like, oh look, HCO3 minus. Yes? The only one I don't want to pick is HSO4 minus because it doesn't act as a base because the arrow does not go that way. Okay, so just watch out for that. Any other one will work. You could use HSO3. You can use HCO3 minus. Whoa, sorry. So we have HCO3 minus, and it's acting as a base in water. So we're going to put it with water because water is amphiprotic. And if it is acting as the base, that means water is acting as the acid. And that means our hydrogen is moving from the water to the HCO3 minus. You wouldn't draw this part, but just to show you what's going on. So we would end up with H2CO3 plus OH negative. And that's it acting as a base because it ends up producing hydroxide. Yes? Now, someone in my other class asked me about this, and they were like, hang on a second, Miss Pants. HCO3 is a stronger acid than water. Shouldn't it act as an acid and water act as the base? Water can do whatever the heck you need it to do. Okay? If you say, I need HCO3 minus to act as a base, water will act as an acid. Okay? Because here's the other thing too, is that water is also a weaker base than HCO3 minus. It's a weaker acid than HCO3 minus. It's a weaker base than HCO3 minus. Yes, because it is also amphiprotic. So it can do whatever you need it to do. Okay? So just don't worry about that aspect of it. Water can just do whatever you need it to do. Okay? And if it says they want that anion to act as a base, then show that reaction. It's not that the other reaction isn't happening. It's just they don't want you to show that part yet. Okay? Jenya, did you fold all that? Oh, wow. Oh my God. And it's an, oh my God. That is beautiful and balanced. Oh my God. Okay. That's awesome. Okay. Sorry. Now that I've gotten over that, not that I'm completely over it yet, but anyway. Anything else? Yes.
Number 6, for written.
Number 6 written, yes. Oh, this is a good one as well. We did this in the other class. Okay, compare the ease with which the first hydrogen is removed from a diprotic acid compared to the ease of removal of the second hydrogen ion. Use an example from the table of acids to illustrate the situation. So what we're going to do first is we're going to say, what on earth is this removal of the first hydrogen? Yes? So we're going to go over here and we're going to say, I've got a diprotic acid, H2A. What is the removal of the first hydrogen? What would I write as the equation for that? What do you want me to write? Donating a hydrogen to who? What? Who? To another reactant. Okay. Who would you like there? Do you know what I would do? I would simplify it and not even bother donating. If you want to have it donate, I would just use water. Yeah, water would be a good choice because then you could then you don't have anything else like cluttering it up. Water is just kind of a neutral background, right? Otherwise you're like, what is the other acid and what's it doing? And like it gets complicated, yeah? So either use water and you'll end up with H3O plus HA minus, or even more simple, just in terms of looking at the species, probably this would be even easier, yeah? So that's removal of the first hydrogen. What is the removal of the second hydrogen? HA in equilibrium with H plus and A minus. This is called the first dissociation. This is called the second dissociation. They come off one at a time when you have diprotic acids, okay? Not like when you have calcium hydroxide, strong base, just all goes to completion. These, they come off one at a time. Now, let's do an actual example of this. So you can, let's go find a diprotic acid on our table of data, because we want to decide which one comes off easier. That's what we're saying. Compare the ease with which the first hydrogen ion is removed. That means which hydrogen comes off easier, the first hydrogen or the second hydrogen, or are they both the same? Right? Do you guys know? Yeah? Yeah, the second one is always like harder to take off. Okay, the first one is always easier, but let's justify that by going and looking at our table of data. Okay, so table of data, let's pick a diprotic acid. Shall we pick H2SO3? Sure, let's do that one. It is right, let's see, we have HSO3, H2SO3. There we go. Okay, so we have H2SO3 and we have HSO3 minus. Our Ka for H2SO3 is 1.5 times 10 to the minus 2. And our Ka, let's call this H2SO3, and let's call this HSO3 minus. Here we go, 1 times 10 to the minus 7. Okay. What am I doing? There we go. 1.0 times 10 to the negative 7. Now, what is Ka really expressing? It is the ratio of the
reactants over products. So
products over reactants. Yes, products over reactants. So a larger Ka value means what?
It's stronger.
It means it's stronger. What does it mean in terms of products and reactants?
There are more products than reactants.
Well, it means not in this case. You still have a number that's less than 1, but a larger Ka value means you have more products than when you have a smaller Ka value. So Ka tells you the position of the equilibrium. Yes, it tells you the position at which the equilibrium sits. This one sits more towards the right. This one sits more towards the left compared with each other. They both sit more towards the left than to the right, but this one is further right than this one. What does that tell you about the hydrogen ion concentration in each case? Or the ion concentrations? There's more hydrogen ion concentration. And this one has less hydrogen. So which one, in which case did you have more easily removed hydrogens? The one where you have more hydrogens. Yes? Now, shall we see if we can express that in a better way than, my Gorbaldy notes? Yes? All right. So let's see if we can do that. So it says, our question says, actually, look at that. It's only 1 mark for that first part. So you don't need to explain it at all for that part. You just need to say the first hydrogen ion is more easily removed than the second hydrogen ion. Okay? So, first hydrogen ion is more easily removed than the second hydrogen ion. So that's part A. Part B is also only worth 1 mark. You don't want to spend a lot of time writing about that. Okay, you don't want to go into huge explanations about what a large Ka value means and what a small Ka value means. You can simply say, in B, they want an example. Example, the Ka of H2SO3 is equal to, 1.2 times 10 to the negative 2. And the Ka of HSO3 minus is equal to 6.4 times 10 to the minus 5. No, 1.0 times 10 to the minus 7. 1.0 times 10 to the negative 7. Therefore, the first H plus comes off more easily, since products are more favored or something. But even that, it's only worth 1 mark. I mean, how much can you say for 1 mark? I feel like if you've got that and you've got that, you could just say, therefore, H2SO3 is a stronger acid than HSO3 minus. And that would do it. Yeah. Yeah. No. Uh-huh. Oh, it should be A2 minus. You're absolutely right. Yeah, that should be A2 minus. Yeah. Sorry, my brain gets a little stupid towards the end of the day. So I get to go to a staff meeting after work tonight. And then immediately following my staff meeting, I have to go meet my girlfriends at the gym because we go to the gym on Wednesdays. So I have to go. That's why I'm wearing like workout wear. So I can just go straight there. So tonight's an exciting night. And then I have to come home and then I have to shower. And then I have to try and write some report card comments. Wednesday is a busy day. That's okay. I'm sure many of you also have busy days in your life. If not today, then other days. All right. Are we good? Okay. Anything else? Do you want to just work for the last 10 minutes? Okay. I have recorded block 7s as well. So if you want to like check it out, you can. We did cover a range of the same questions. So especially the written ones. So I'm quite pleased about that. You guys had similarly good questions to produce. Yes.